Okay, welcome back guys. We have seen in the previous video the potential due to a dipole. So now let's go ahead with more of the properties of the potential. So in this video we'll cover three topics, and the first one is about equipotential surfaces, like what are equipotential surfaces and what are their characteristic features. And then we'll see the relationship between electric field and potential. And lastly we'll see a generalized method of finding the work done due to a arranged configuration of charges. Okay, work done is basically the potential energy of that configuration. So I have written down the timings at which these topics are going to be found. So if you want, you can directly skip to that topic. Okay, so let's start with the first one, which are equipotential surfaces. So what are equipotential surfaces? Okay, so let's first see what are equipotential surfaces. So an equipotential surface is any surface about a charge in which the potential is a constant. The potential does not vary. So if you talk about a unit positive charge, the equipotential surfaces are going to be concentric circles around it. So these are going to be the equipotential surfaces. This is a surface, this is a surface, this is a surface, this is a surface, this is a surface. As you notice, they are more closely packed from the beginning, closer to the charge, and as you move out, they become more widely packed. So these are called equipotential surfaces. Each one of them is an equipotential surface and not the entire arrangement. That is, let's consider the last loop. The potential at this point, VA, is equal to any point on this circle. The potential at this point, for example, VB. So the potential at these 2 points, VA and VB, are equal. And this is a characteristic feature of only this equipotential surface. Similarly, you can take a different point, VC and VD. And VC and VD are equal. So equipotential surfaces are those surfaces in which the potential is constant throughout. Okay, so we saw one example of equipotential surface, that is for a positive charge. Now let's look how will a equipotential surface look for an uniform electric field. That is in this case. So how do you think the field is going to look like? How do you think the equipotential surface is going to look like? It is planes parallel to the perpendicular to the field lines. It's going to be in this way. This is one equipotential surface. This is another equipotential surface, this is another, and so on. It's just planes perpendicular throughout the field. At each and every points of these, like one plane correspondingly, the potentials are equal. Then a different plane over here, potentials are equal. So this is how you draw a equipotential surface. Now the characteristic features, the conditions for surface to be satisfied as an equipotential surface is that it should have constant value of potentials throughout the surface. This is one condition, and the other condition is that the given surface must always be perpendicular to the electric field vectors at that point. So these two are the conditions for any surface to be qualified as an equipotential surface. This second point, let's see logically, let's see with an example why it must be true. So if you want, you can note down these two. So let's consider an equipotential surface. Let's say this is the charge and this is the equipotential surface, for example. So if you want, you can recheck the second point. How is the electric field lines for a sphere or for a charge? It's in this direction. So whenever it is coming radially outside, it's always perpendicular to the surface. This was the second point, right? So, but why must it be? Why can't it be different, not perpendicular, but instead a line like this? Why can't this be the electric field line and still disqualify as an equipotential surface? So here's the answer. If this was the equipotential surface, and if that was the electric field lines, then you can clearly see that there exists a non-zero component along the horizontal direction. Like you can resolve this vector among two components. One is in this direction and the other one is in this direction. And what's the reason of doing this? Why we are trying to do this is to prove that if you need to move a charge from this location to this location on the equipotential surface, logically, theoretically, the value should be 0 for the work done, because the potentials here are 0. We know that work done equals the difference in the potentials. So if you want to move a charge from here to here, work done must be 0 because the potentials are equal. That is how it should be for a equipotential surface. But in this case, you can see that there exists a force over here, which is in the horizontal direction. So if you try to move a charge from here to here, you have to do work against this present force. So why is this force not counted? Because work done is force dot displacement, that's Fs cos theta. When cos 90 degrees, this is in 90 degrees, cos 90 becomes 0, and this is why perpendicular vectors do not contribute to work done. And that's the reason why a non-perpendicular vector, as in this case, gives rise to a horizontal component which will cause a work done. And if it causes a work done, it does not qualify for a equipotential surface. So that's the second condition. All electric field vectors must be perpendicular to the given surface. Okay, so now we saw what is an equipotential surface. Let's go ahead to the next topic, which is the relationship between electric fields and potentials. The topic that we're going to discuss now will be helpful in a lot of reasoning type of questions. So there are two points under this topic. That is, first one, the electric field is always in the direction where the potential decreases the most steepest. So this is the first point to keep in mind. The electric field is always in the direction where the potential decreases the steepest. Like for example, if let's say you have a region over here. This part of the region has a potential of 5 volts. This part has a potential of 3 volts. And this entire part has a potential of 1 volt. So what would happen is, you can't expect 5 volt, the direction of electric field lines to be in this way. Instead, both of them would give electric field lines toward the 1 volt in this direction. So that is what the first point says. Electric field lines are always in the direction where the potential decreases the steepest, the highest difference. So that's the first point. And then let's look upon the second point, which states that electric field is given by the change in the magnitude of the change in the potential divided by displacement. So this comes directly from the first formula that we have written, that potential equals ER. This is just a way of expressing that electric field, the magnitude of the electric field is equal to the magnitude of change of potential per unit displacement. DL stands for unit displacement. So these two are the points for the relationship between electric fields and potential. So you can note it down. And next we'll go to the third topic of this video, the final topic, that is the work done due to a charge configuration. Okay, so now this is the third topic, that is potential energy of a system. Not to get confused, where we previously discussed that was potential due to a system, where we added up the individual potentials, but this is potential energy of a system. So let's say we have to bring two charges. Let's first consider the simple case where we have to arrange two charges. Let's find out how much is the potential energy stored in the system. Initially, both the charges are at infinity. So let's say this is charge Q2, Q1. Both are at infinity. You have to bring them over here. That is, let's consider a coordinate axis. The first point you're bringing is always going to be at the origin, because you're going to keep that as the reference point to which you're bringing the next charge. So Q1, let's say we're bringing Q1 first, and I'm placing it at the origin. That's the coordinate axis is just for easy understanding. With reference to Q1, we are bringing Q2. So, or else let's just get rid of the axis. You don't need this. Let's bring Q1 into the region first. There is going to be no opposition to this Q1 because there exists no electric field initially. if there was a charge, that is what is going to give rise to electric field. But there is no charge right now, so you can bring Q1 easily with zero work done. So let's divide the steps. The steps are going to be work done to bring Q1, step 1, and step 2 is work done to bring Q2. When you add these both results, this is what results in total work done, also known as potential energy of the system. This total amount of work done stored in the system is the potential energy of the system. So let's calculate. Work done to bring Q1 we found out to be 0 because there exists no force to oppose. But work done due to Q2 exists. What is this work done? So let's try to calculate the work done due to Q2. So let's see what is the first step. We can use the formula that work done equals VQ, which is what you learned in grade 10, that work done is the potential times the charge. So what is the potential? So the work done to bring Q2, I write it as work done 2, and this is work done 1 equals 0. This is the first result. So we are using the equation that work done equals potential difference times Q. So the potential due to the first charge. What is the potential due to a charge? We had discussed this in the previous video. It is 1 by 4 pi epsilon naught Q by R. So Q1 this is, and what is the charge? You have to make sure that this potential difference, I'll mark it over here. Potential difference V due to present charge. And Q is the charge you're bringing, charge brought in. So these two are not for the same charges. The first term potential is the potential that is existing due to the charge that we brought first, Q1, which is 1 by 4 pi epsilon naught Q1 by R. And the second is the charge that you're bringing now, that is the second charge, Q2. And this distance R is the distance separating them. So I'll just call it R, where R is the distance separating Q1 and Q2 and Q2. So this is the total work done, because we have added this to 0 but doesn't make a difference. So this is the total work done in bringing those two charges and assembling it at a distance. And this is also equal to the total potential energy of the system. So in short, potential energy of the system is the total work done it takes to arrange the system into that configuration. Now let's look at the different case. This was with two charges. So let's quickly look at how much it would take for bringing three charges. So let's first consider Q1, Q2 and Q3 are at infinity, and you have to assemble them in this form. I'll name the distances as R1, R12, R23, R13, corresponding to the numbers they are. So what is the total potential energy of the system? Let's do. So the step 1 steps are work done 1 plus work done 2 plus work done 3 equals 0, where each of them are the work dones to bring each of the charges. But here there's going to be a different case. So let's look at that when we do. What's the work done to bring the first charge? Which is 0, because it is the first charge, there exists no extra field. So there's going to be no repulsion, no opposition to bringing this charge. What is the work done to? That is when you bring the charge Q2. It's not equal to 0, it's plus another quantity is here, and this is equal to the total potential energy. And you'll find out what is the total potential energy. So what is the work done to? That is to bring charge Q2. When you're bringing charge Q2, these are not there, so avoid this. It's only the field due to the potential due to Q1, which is 1 by 4 pi epsilon naught Q1 Q2 by R12. Okay, this is what we discussed. This is basically bringing these two charges is basically what we did in the previous case, that is two charges. Now we are bringing the third charge. So when you bring the third charge, there's going to be both Q1 and Q2 opposing. So this extra quantity that was missing is the work done due to the second charge. So this is going to be work done due to the first charge, and this is going to be work done due to the second charge, and together they contribute for the work done to bring the third charge. I think there's a problem with the notation, so let's just change the notations. This is the work done to bring the first charge, work done to bring first charge WQ1, work done to bring second charge, work done Q2, and this entire thing is work done Q3, where the sum of the work dones individually for 1 and 2 are being added up. So why does this happen? You already have two charges and you're now bringing the third charge. So this is going to experience the potential effect of both Q2 and Q1. So how is that going to be? What is potential due to Q1? 1 by 4 pi epsilon naught Q1 Q3 by R13 plus the potential due to the second charge, which is already present, which is 1 by 4 pi epsilon naught Q2 Q3 by R23. The sum of all these is the total potential energy. That is, potential energy equals 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 divided by R13 plus Q1 Q3, it's Q1 Q2, Q1 Q3, Q2 Q3 divided by R23, and this is the total potential energy of this system. So you can find it out for any number of charges. All you need to keep in mind is that the first charge you bring will experience no work done is 0. The second charge you bring is going to experience, due to the first charge which was already present, so it's multiple of the charges. The third charge you bring is going to have an effect due to two charges which are earlier present. Similarly, the fourth charge due to the three which are previously present. So, and then you add all of the work done, it's going to be the total potential energy of the system. So this is it for today's video. In the next video, we'll see the topics of several topics like how the dipoles, what's the potential energy stored in a dipole, and etc. So I'll see you all in the next video. Thank you.